So I'll talk about two z-tests. Okay. So it is to test if sample mean is significantly different from a known population mean. So this is your one sample z-test. One sample mean is implicit. So this is all for comparing means only. So this is to compare sample mean to population mean. Sample mean is your x bar and this is your mu. That's what it compares. And for all the tests there will be a test statistic. So what is the test statistic for this? So this is called Z. Like for t distribution it was t, right? So this is called Z. Okay, and this is equal to. So as I told earlier, the numerator will always be a difference of the means when it is a mean test, and the denominator will be some form of standard deviation. Here it is sigma by root n. Okay, so this is your sample mean. We know this. This is your population mean or a known mean, some true value. Okay. This is sometimes 0, may not also. This is your sample size, and this is your known population standard deviation. Population standard deviation, and this denominator term. If you check my central limit theorem video, we have discussed a lot about this. That's what I was mentioning at the start of the video. This sigma by root n. This has also got another name, that is, it is called standard error. Standard error. Okay. What is standard error? We have discussed there. I'll just give you a brief about it. So this z statistic, so it will follow some distribution. So it follows a normal distribution. That's where the z score comes from. Okay. So this z statistic will follow follow a normal distribution. We'll write that also. So the distribution, underlying distribution is normal or Gaussian distribution, like bell shape, standard bell shape curve. Okay, and standard error, what we mean here, this is a standard error. Okay, so this, whatever is the population standard deviation, this is divided by square root of the sample size. This is called standard error because this gives us the standard deviation of sample means. Okay, this is a standard error. If you remember central limit theorem, when we took multiple samples and we did, we have samples, right? So we have samples x1 to xn, trial 1, trial 2, x1 to xn. Like this we did k trials, x1 to xn, and then we had x1 bar, we had x2 bar, like this we had xk bar. Okay, so we have this n sample means, sorry. Remember from the central limit theorem, so we have this n sample means, and when we plot this sample means, this will follow a Gaussian distribution with mean mu, and same, it will converge to the population mean, and the variance will be sigma square by n, and the square root of this was the standard deviation of the, and this sample means follow a Gaussian distribution. And this is the variance of that, and the square root of that is the standard deviation of the sample means. Okay, and you have done the derivation also for this. Check that. I'll put the link in the description. So this is what it means. It is the standard deviation of the sample means, and the standard deviation of the data of the population data is sigma. But for the means, this is sigma by root n, and that is called standard error. I hope standard error is clear and it's revised again. Okay, and what is two sample z test? So this is your test statistic. Simple. Here, similarly, what is a two sample z test? So we have, in one we are comparing just sample mean to population mean. Similarly, when we compare two independent samples, we have two groups and we want to compare the means of the two groups, then we use two sample mean test. So we write two sample, I'll skip the mean, two sample z test. Okay, so this is used to compare means of two independent samples or two independent groups. So I'll just write it, compare means of two independent samples. Okay, and the statistic associated with this would be, this is 2 sample, so what will be the test statistic? Again, the difference of the 2 sample means x1 bar minus x2 bar divided by standard deviation in some form. Okay, so this will be a sigma square by n1 plus sigma 2 square by n2. Okay, the square root is this, so this is your, these are your sample means, and then we standardize it by, so if you take square root of, these are variances, right? These are population variance which is known for both the samples. When we scale it, we divide it by n1 and n2 so that it's standardized, and then finally we divide it. So this whole term will be acting as sigma or standard deviation, and the units of both will be same, and that's how we standardize the test statistic. So as I mentioned earlier, all the test statistic will be some form of mean. If it is comparing means, it will be mean by some form of standard deviation. We have seen this in t-test also. Okay, so if this is there, if this is understood, okay, simple. Now let's do a quick problem to understand. Right? This z-test is very simple. Okay, the only thing is tricky part is many people don't understand how to check the z-score table. I'll show you that quickly, but let's do a problem now. So we have the known population mean of the ML model is 1/22. Okay, I won't make it one more. So your mu naught, this is your known population mean or the existing runtime of ML model. The existing runtime is 120 seconds. Okay, and after the new optimization, a new optimization was applied. So new optimization is applied. And now this changed to 117 seconds. Okay, and the sample size for one sample only. So the sample size is how many samples we took? That was 100. So n is 100 here. Okay, 100 runs. We did 100 runs and we found out that the new runtime was 117 seconds for that model after the optimization was applied. Now, does the optimization have a significant impact on to reduce the runtime or not? We need to validate this claim. So did the optimization have the impact? Did the new optimization, so this is a hypothesis testing, did the new optimization have significant impact to reduce the runtime? Okay, so that's the question, and we will see, we'll put the alpha or significance level as 5%. This is your significance level. So we'll follow the standard template of hypothesis testing. We'll go one by one, and so that it becomes very clear to you. And if you have not seen the hypothesis testing video, please go and check that. That has all the details, how to do, what does all the term mean. So we start with, what is the very first step for any hypothesis testing? We start with what is the null hypothesis and what is the alternate hypothesis. First of all, fix this. So my first alternate the null hypothesis is that nothing has changed. Always it maintains the status quo, means your runtime has not improved, it is same. So your mu still remains 120 seconds, no change. Okay, and my alternate hypothesis is that it has reduced, right? So we have found that this is 170 seconds. So my alternate hypothesis is that whether it has reduced significantly due to the new optimization or not. So my alternate hypothesis will be that it is less than 120 seconds, whether it has reduced or not after the optimization. This is the claim we need to validate, and we have this 100 samples or 100 runs. We did 100 runs and we got some data, and the mean of that data was 117, and using the z-test, one-sided z-test, will confirm this. Okay, so what is my test statistic for one-sided z-test? So because we are just comparing from the sample mean we are ascertaining the population mean. So my test statistic is Z, this is equal to X bar, and what is my X bar here? Sample mean after 100 runs is equal to 117 seconds, and N is equal to 100 runs. 100 times I have run the runtime. So this is what it is, minus mu by my standard error, sigma by root N. What is sigma? Sigma was given, okay, population standard deviation. Okay, we missed it in the problem, so let's write that. So sigma is let me write down here. So the known population standard deviation, no optimization. Okay, sample size is this, and population standard deviation is equal to say 15. This is your sigma. Okay, so this is your standard deviation. 15, 100, 117 seconds, 120 seconds was the population mean. This is your X bar, this is your sigma, this is your N. All the parameters are here now. Now let's just put it in and check with the z-score. So this is a null hypothesis that nothing has changed. The runtime is still 120 seconds. Alternate hypothesis is no. After the new optimization, it had an impact and it reduced the runtime below 120 seconds. Okay, now let's compute it quickly. So what is z statistic equal to? 117 minus 120 by sigma is 15 by square root of 100. This is equal to minus 3 by 15 by 10. 5 3s are, okay, 5 3s are, and this is 5 2s are. Okay. So this 3 and 3 goes off, and then this will come out to minus 2. So my z statistic, okay, observed is equal to minus 2. And what was my significance level? 5%. Okay. So this is one-sided because we are comparing less than. So less than is left side. This is coming as negative. So my mean is less than. If it would be greater than, I'll go to the right sided test, and if it is less than, then we'll go to the left sided one-tailed test. So if you don't understand this, check my hypothesis testing video. What is one-sided tail test or two-sided tail test? So for example, this is my mean here, whatever is the mu. Okay, if it is less, okay, here this x bar is less than this. This is what we are doing, that x bar is less than mu. This is my alternate hypothesis, x bar is less than mu. That's what we are saying, that this is x bar. That's what we want to ascertain. So this net value, anyways, we have got minus 2, so this will come to the left side of the, because the value will be negative, this net value, because the bottom, this is always going to be positive, so numerator will decide whether I go left or right. If this would have been positive, if I was saying that x bar is greater than 120, then I'll go towards the right, because the values that I will get in the observation of the test statistic would be positive, and since it's negative, we'll go towards the left side. So we have found out that this is somewhere around minus 2, right? So this is minus 2. So and what is our alpha? Alpha is 5%, so that is 0.05. Now let's check the z table. Okay, so this is so the p value here, so there will be p value. So we have done steps. We found out what is our null and alternate hypothesis. We fixed that. We computed our test statistic. We saw its distribution. Then we found out what is our alpha. Then we'll calculate our p value. So the p value would be area under the curve here. This is our p value. On this side, to the left of this. And now we have to find out the significance value is there. So now what is T alpha? This is the critical value. So this is your critical value, for which my area under the curve will be less than 5%. Okay, less than 5%, and 5% will be 0.05. So let's see the z-score table. So if you see here, I've opened the table. If you just go and Google z-score table PDF, you will get the table. Okay, I have opened one table. So here, if you see, there are important hypothesis testing critical values. It's written already. So if the significance level is 0.05, if you see here 0.05, what is the corresponding value for the left tail test? minus 1.645. We'll just take it from here itself. So my critical value here will be equal to minus 1.645. So this is your, here mu is 0, right? Because this is centered, mean centered variance scale. 0 is 0. For Z score also everything is centered as 0. N 0 1. So my, and this is minus 2.0 whatever, and my this thing comes out to be, the T alpha comes out to be, this is T alpha, and this is equal to 1.645, and my critical value is this. So my area under the curve to the left of this will be 5%. This is my significance level. But if you see, my observed, T observed or Z observed is towards the left, so the area under this curve would be definitely less than 5%. Means, what does this say? That P value is less than alpha or 5%. So this is less than the significance level. So what do? We reject null hypothesis and accept alternate hypothesis. And what is our alternate hypothesis? That there is a significant evidence that the runtime, okay, is below 120 second. It has this new optimization has improved the runtime and it is below 120 second. That was our alternate hypothesis. Where was alternate hypothesis? Yeah, here. So we accept this. Yeah, due to the new optimization, my runtime has significantly reduced and it is now below 120 second. We accept this alternate hypothesis because we rejected our null hypothesis. Okay.